Radioactive particles and energy are harmful to us. That's energy on the higher end of the electromagnetic spectrum that includes UV, X-rays, and gamma rays. So remember, all this is lower. So the lower energy that does not cause any harm is called non-ionizing radiation. Remember, it's all called radiation, but this is the harmful radiation, and the harmful radiation is ionizing radiation. What that means is that these waves of energy from UV, X-rays, and gamma rays can cause molecules to turn into ions. For instance, when a beta particle hits a water molecule, it will cause this water molecule to form a water ion and then release another beta particle. So this is similar to the chain reaction that this beta particle then released can go on and start another reaction, and this addition, the water molecule that's ionized can also react with any water molecule, regular water molecule, or that ionized water molecule can react with DNA, and when it reacts with DNA, that can permanently change the DNA and lead to mutations and cancer. So ultimately, this is how radiation causes cancer, by causing molecules to form ions in the first place. Remember that radioactivity includes alpha particles, beta particles, and gamma rays. And alpha particles are these large, relatively large helium nucleus. So the helium nucleus cannot actually travel that far, and it can be easily blocked, sometimes by just a piece of paper. A beta particle relatively is slightly larger and can travel farther, but also can be blocked by materials like wood, cement. Gamma rays are the most dangerous because not only can they travel long distances, but they can also pass through many types of material like wood. So this gamma is what we need to protect ourselves from. You do that by basically not being exposed to gamma rays, and this is what we talk about when radiation is dangerous. Radiation is used to treat cancer because it kills rapidly dividing cells, including cancer cells, but also rapidly dividing cells like hair and stomach lining. The ionizing radiation affects all cells, but only those rapidly dividing cells, the cancer, the hair, the stomach lining. Those are the ones that are really damaged because other cells can repair or sustain the damage. Radiation sickness, in contrast, is an illness that's caused by ionizing radiation as well, but it's long-term. So radiation treatment is just a short amount of time, scheduled appointments, and allowing the body to recover. But radiation sickness is long-term exposure to radiation that we try to avoid. Radioactive isotopes are usually large atoms that are naturally unstable due to the large size, having so many protons and neutrons stuffed into the nucleus. So all elements higher than polonium, that's atomic number 84, are radioactive. Some lighter elements have naturally radioactive isotopes as well. So that includes the hydrogen 2 and the carbon 14 we talked about in chapter 4. A radioactive isotope will decay and release radiation over time, and this is an example of uranium-238. This is a natural radioactivity that is around everywhere because uranium-238 is common in dirt and soil, and things made out of dirt like ceramics. So uranium-238, natural radiation that you have outside your door. So this is a 14-step decay series. That's what's shown here. And what happens is uranium-238 decays over many years. I'll look at that. But this is each arrow kicking out an alpha particle. This is a red arrow. A blue arrow is kicking out a beta particle. And so each step is one decay release of radioactivity, either alpha or beta. And the end product, okay, is that you have one step change to a different step change to a different element, each time releasing an alpha particle or beta particle. And the end product is this lead-206, so that's Pb206. And that doesn't happen in seconds or minutes or hours, but over millions of years. An individual uranium-238 takes millions of years to go through all these steps, and along the way is releasing alpha particles and beta particles the whole time over the millions of years. So how long does an isotope uh, remain radioactive? How long is it kicking out radioactivity for? Well, it depends on the isotope, the radioactive isotope. Some decay quickly and some take millions of years. This is indicated by the half-life, what's called the half-life. Each radioactive isotope, each radioisotope has its it has its own half-life, okay, and this is inherent to the isotope itself, and the half-life is T 1/2 is the symbol, and what it means, it's the time, that's T, that's required for the radioactivity that is originally present to fall to half of the original amount. So this is a constant dependent on the radioisotope. So the uranium-235, to get to half of the original radioactivity, takes 4.5 billion years, 4.5 times 10 to the 9 years, okay? And this is what is in the uranium fuel pellets in a reactor. So that's why there's an issue of nuclear waste. That's spent fuel that still has radioactivity. It's going to be radioactive for millions of years later. So this is in comparison to something like polonium-214. This is only emitting radioactivity for 0.00016 seconds. Okay, so the half-life is dependent on each radioactive isotope. How long a substance is radioactive for depends on its half-life, and remember the half-life is when you have one half-life that has passed, it means 50% has decayed, and 50% of the original 100% radioactive is remaining. So you have half of it has decayed. So each half-life represents a breaking down to just half of the original, but the original doesn't start at 100%. Now you have only 50% left, and so this will decay another 25%, and that adds up to 75% of the total decayed, but you still have the 25% left. So the thing about half-life is basically you get halfway there each period of time, each T 1/2, you get halfway there, and as you get closer and closer to zero, okay, this starts to kind of the curve levels off, and this actually doesn't, it takes a lot longer to decay when you get closer and closer to zero. And after 6 half-lives, you still have some percent remaining. But when you're talking about a very long half-life, like the uranium-238, that it takes 4.5 billion years to get to 50%, well, we basically have all this radioactivity present in our lifetime and many other lifetimes beyond, because the half-life is so long, and if you just keep counting out, it takes a long time to get to zero.